Okay, so in this video, I'm going to do a few more examples in which we'll work with logarithms. And the first example that we have right here, it says, well, express as a single logarithm, and what are we supposed to express? 1/2 the log of x minus 2 minus the log of x minus 3 plus the log of x squared minus 5, and we should have a close bracket right here. So there it is. Okay, well, to do this, we're going to use some of the properties of logarithms that we discussed in class, namely these three that we see here. The first says that the log of a product is equal to the sum of the logs. The second one here, it says that the log of a quotient is the difference of the logs. And the third one here says that if you're trying to take x times the log of y, then you can take this x here and move it over here as an exponent on y. So we get to bring that upstairs here. And we actually proved that in class. All right. Note in particular that because the natural logarithm is just a particular logarithm, it's log base e, where e is this special number that we talked about in class. So all of these three properties definitely also hold for the natural logarithm, ln x. All right, so back to the question. Here, we're supposed to express this quantity here as a single logarithm. So let's do that. Looking first, right here, we see that we have the sum of two logs, and we can write that as the log, the single natural log of the product of x minus 3 and x squared minus 5. So let's do that. And also, when I do this first step, we'll notice that we have this exponent. We have this constant here multiplying the logarithm, and we get to bring that up over here as an exponent. All right, so let's do that. This then is equal to, bringing that exponent up, the log of x minus 2 all to the power 1/2. There it is. And minus, and now we have the log of this sum, remember, and we'll write this as the log, rather the sum of these logs, and we'll write this as the log of the product. All right, so this is minus the log of x minus 3 times x squared minus 5. All right. And now, what will we do? Well, now we have a difference of two logs, and we can write this as a single log of a quotient. And notice also we have this to the power 1/2, so I could write that as the square root instead of x minus 2. So I'll do that. That's not really necessary. All right, so now this is equal to, then, let me just move this down. This is now equal to the log of square root, writing that power 1/2 as a square root, x minus 2, and the difference of logs we write as the log of the quotient. So in the denominator, we're now just going to have x minus 3 all times x squared minus 5. And that's it. We've now written the logarithm that we started with up here as a single logarithm. We have one log here, we had 3 logs up there. Okay, so now let's do another example. Let's see, I'll write this. Okay, so another example, e.g. says solve for x. Okay, so here we want to solve for x, in places where we see an exponential function or maybe a logarithm. Okay, so what's this going to look like? Maybe I'll head further up. First one is A. It says e to the 2x plus 7 is equal to 7. Okay, so we have this x here sitting as an exponent, and somehow we need to solve for x. And if we want to solve for x, somehow we've got to get rid of this e, this exponential function. Well, if you're trying to get rid of an addition, you'll use subtraction, the inverse operation to addition. If you're trying to get rid of a multiplication, you would use a division, the inverse operation to multiplication. And when you're trying to get rid of an exponential, you take logarithms, because remember, the logarithm is the inverse to an exponential function. So in particular, maybe we'll write this over here, remember, what do we have? Well, we have that, little recall then, that we always have that a to the log base a of x is always equal to x, provided that x is in the domain of that logarithm, which is to say provided that x is bigger than 0, and log base a of a to the x is always x. This is because the logarithm and the exponential function a to the x are inverse functions. That's for any x for which a to the x makes sense, which is to say any x at all. So in particular then, because we know that the natural logarithm is just log base e, in particular then we have, so a little therefore, e to the natural log of x is x, okay, for x bigger than 0, and the log of e to the x is always equal to x for any x in R. Alright, so if I want to get rid of an e to the x, I can just apply the logarithm, the inverse operation to e to the x. And if I want to get rid of a natural logarithm, I can just apply the exponential function, the inverse operation of forming a logarithm. Okay, so back to our problem over here. We have e to the 2x plus 7 is equal to 7. I want to get rid of this e here in order to solve for x, so I'm just going to apply the logarithm to both sides. Alright, so we can say then that if e to the 2x plus 7 is 7, then the log of e to the 2x plus 7 must equal the log of 7, right? I took the log of the same number on either side. And now, using the fact that the logarithm and the inverse function, there they are, log e, what happens? Log e, they cancel each other, as we said. Okay, so coming back over here, what can we say? Right here, log e to the 2x plus 7, the log and the e cancel each other. We're just going to be left with 2x plus 7. Alright, so 2x plus 7 is what we have on the left. And on the right, we just have the number log of 7. Now, I can just solve for x in the usual way. So I'll subtract 7 from both sides. We'll get that 2x then is equal to the log of 7 minus 7. Alright, brackets here indicate I'm only taking the log of that first 7. And now to get x, we can just divide both sides by 2. X then is equal to, I'll write it like this, 1/2 of the log of 7 minus 7. That's all there is to it. So the point then is, if you wish to get rid of an exponential function, what do? You just take logarithms. All right, let's do one more example. Okay. And so example B. It says solve for x again, and now what we have is log of x squared is equal to pi. Okay, so, and what do we want? Well, we are trying to find what is x. Maybe that's a bit of an ugly pi, so let me clean that up a little bit. What do I do? Oops. Okay, so pi now is all cleaned up. All right. So remember, we are trying to solve for x here, and we then need to get rid of this logarithm. So, as said before, we need to apply the inverse of the logarithm function to get rid of it. And, well, what is that? The inverse of the logarithm is the exponential function. So we're just going to apply e to both sides of the equation over here, and that will get rid of our logarithm. All right, so what do we have? Back here, taking e, both sides. If log x squared is pi, then e to the log of x squared is just e to the pi, and now we have e and the log together. They cancel one another, and I'm just going to be left with x squared here on the left. So we have then x squared is equal to e to the pi, and therefore x can take one of two values. Either x is the square root of e to the pi, or, namely the positive square root of e to the pi, or x is the negative of the positive square root of e to the pi. So let's just write that down. That means then that x, therefore, is equal to plus or minus the square root of e to the pi, which is to say plus or minus e to the, well, this is e to the pi to the power 1/2, which I can write as e to the pi over 2. Okay, that's all.